Hello and welcome to another episode of It's Good to Know. And my guest today is Brad Prezant. Brad is an occupational health scientist, experienced in public health issues, and he works primarily as a consultant, doing university-based research. He has functioned for many decades as an independent expert or an expert witness in Australia, New Zealand, and the US. Brad is a certified occupational hygienist and has previously maintained certification as a certified professional ergonomist. Brad is the current vice president of the International Society of Indoor Air Quality and Climate. ISIAC is how I think it's pronounced. He's also an accredited well building professional and a well advisor board member. Brad was the chief editor of Recognition, Evaluation and Control of Indoor Mould 2007, the American Industrial Hygiene Association, IAHA, which is an organization that supports mechanical engineers in the hygienic design of ventilation systems. And most recently, he is involved in the 2021 publication of the ERA's Guide on Schools and Ventilation to Prevent COVID Transmission. Mr. Prezant has generated many technical articles and papers, both peer-reviewed and read for more common consumption, and has spoken extensively at industry and professional society conferences, including the recent AMCA conference in Melbourne. Brad has recently served as an independent expert and has been assisting various states in their preparation for the hotel quarantine issue. And in particular, some of the early, challenges that system had, and then some of the rectification steps. Brad, that is a very humble way for me to introduce you, but I'm going to ask you to elaborate a little bit on my introduction of yourself. I'm just so delighted to have you on the show. Would you mind sharing your enthusiasm for this topic with our audience, please?
Well, thank you very much, Rob. It's a pleasure to be here. Indeed, I'm a public health scientist, and I have sometimes one foot in the mechanical engineering world as it pertains to ventilation and air quality, one foot in the public health world. And I guess, as odd as it may seem, in order to be effective in my field, I have to have a few extra feet. Because dealing with indoor air quality is a very multidisciplinary issue. If we're dealing with mold, we're talking about microbiology. If we're dealing with particles moving through air, we're talking about understanding pressure differential and particle physics. So those of us who work in this sphere really have to have a bit of a multidisciplinary background to be effective.
It's a funny thing, isn't it? It's the challenge of going deep into a topic as well as being diverse across the topics that you are across. So I certainly understand that. Now, Brad, some of our listeners will think of mold and they'll think of exit mold and ads they've seen on television and people squirting sort of reasonably toxic chemicals around their bathroom. Would you mind taking us through a simple description of mold, both from the relatively benign stuff to the deadly stuff, and give us a sense on the spectrum of the sorts of molds that we encounter in buildings?
Well, to be honest, I'd prefer to talk about indoor dampness than mold. And I say that because the issue is really indoor dampness and our failure to manage moisture in the built environment. So whether it's a plumbing leak, a roof leak, whether it's a condensation related issue, whether it's how the wall assembly was manufactured and how it permeates vapors or captures them and allows building materials to degrade, really it's all about moisture. And if we look into the health literature in terms of, what are the consequences of that moisture? I mean, we know buildings degrade, and that's a good reason to keep them dry and manage moisture in buildings. But there are issues with health when people live in damp housing. And we talk about mold because mold is the visible manifestation of indoor dampness. So when you have water, you have, in essence, the beginnings of a biological spark, because all the materials in our built environment that are organic, in other words, wood-based products or anything that's natural, as opposed to stone or some other non-organic material, concrete, All of these materials are intended and designed to be degraded by molds. But when moisture enters, a cacophony, if you want to think of it as that, a symphony with hundreds of different instruments begins. Like a biological spark ignites a firestorm of activity. Along with molds, we're going to get bacteria. And then we start building a food chain, because if the molds start to grow, there's going to be invisible mites that feed off the molds. There's going to be things that are feeding off of the mites that are feeding off of the molds. And eventually you end up with an ecosystem. And there might be cockroaches, there might be rodents, et cetera, all of which is beginning with this biologic spark of indoor moisture. So we see the mold, but think of it as a sentinel. Think of it as the canary in the cage that's saying, we have biologic flotsam and jetsam floating around here. And I'll talk more about that conceptually. But basically, the mold is the visible part, but all sorts of other stuff is happening as well.
That's a good segue, because the other topic I wanted to kind of mash up here was to talk about virus transmission. I think at the top of head is the various strains of coronavirus that people are dealing with, and how to deal with that. But prior to SARS-2 or coronavirus 19, we've always had, I guess, some struggles with providing an environment that is resilient to virus transmission. Could you talk about some of the issues there? And I'm talking about just for the people in the construction industry, that they can get a sensible handle on virus transmission and the issues.
Okay. Okay. So when we talk about infection indoors and how the built environment either enhances or detracts from infection, that's never been on people's radar screen. So, I mean, except in, for example, healthcare institutions where we know we might be dealing with persons with airborne diseases that have to be isolated. But other than that, really specific occupancy, this has never really been on our radar screens. So if you talk to people who operate buildings, facility managers or HVAC mechanics or whatever, their criteria for accountability has always been reducing hot calls, cold calls, any complaints, and keeping the costs as low as possible. That's what we've asked them to do, and they've done a great job of that. The designers have designed buildings that create comfort and minimally use energy. So when we talk about a building as being designed for or intending to minimize infection transmission, that's never been on anyone's radar screen. Never mind the people who do this, like, for example, in ISIAC and other indoor air scientists have been looking at this issue for decades. And there's been some great work done showing how the built environment either enhances or detracts from infection transmission. But it's never been on anyone's radar screen until the last year or two. And even then, obviously your listeners are aware how much those of us who went through the SARS-1 and understand airborne transmission of respiratory viruses had an enormously difficult time getting the political and public health authorities to pay attention and accept the fact that SARS-CoV-2 was airborne. That's a story we probably want to pass over briefly, but as you know, it was an enormous struggle. And here in Victoria, it led to massive issues with hotel quarantine escapes. It led to massive issues with infection in aged care, et cetera. But, the dimensions of a room and the frequency in which the air is being refreshed in that room and the patterns of flow in that room all are going to determine what the infection potential is, along with personal factors like your breathing rate, like your inhalation rate, both exhalation, inhalation, your activity level. These are all going to determine the risk.
Sorry there, Brad. Brad, you touched on, I think, the third leg in this chair that I'm hoping we can sit on today, and that is there have been some critics around the ASHRAE response and the SIBC response, that the measures that are put forward are in strong contradiction to what is affordable to retrofit in a HVAC situation, but also in terms of people's carbon budgets. They're striving towards carbon neutrality, and at the same time, we're talking about extra fresh air and extra filtration and purging and all sorts of other energy-intensive measures. On the board of ISIAC, I'm presuming this is a red wine, bottle of red wine debate that is occurring regularly. This tug of war. Can you lift the lid on that and just describe what are the conversations that are being had? Is there a prioritization of mold and perhaps COVID transmission as being much more important than energy? Is it seen as a short-term, temporary thing, and in a few years we can get back to focusing on carbon, or is it always that we must strive towards carbon neutrality, and these other measures need to be perhaps adoptable and quickly adoptable, and therefore be easy to adopt, so to speak? Can you see the tension
Oh,
around those two?
absolutely. Absolutely. You mentioned in my intro that I was involved with the Well Building Program, which is really all about sustainability and health. As an assessor, a well assessor, and a well accredited professional and an advisor to that community, I'm strongly supportive of sustainability issues. I think it's a big fallacy to think that we have to have infection control in some way opposed to sustainability, because there are many solutions that encompass both. So to set up that false, no sum game makes no sense. I'll give you some examples. Since we have a ventilation oriented audience, generally the model that we generally use for buildings and mechanical ventilation is a turbulent mixing model. We have supply diffusers that bring the air in at relatively high velocity, disperse it in the room in such a manner that it will induce room airflow, bounce off the walls, create circular mixing. That's how we have always ventilated buildings. And the reason for that is that it creates a pretty uniform hot and cold environment and minimizes stratification. That's assuming we don't have a VAV system at 10% of maximum flow with supply diffusers and return diffusers at the ceiling. But let's talk ideal. But there are other types of designs that have been being implemented for decades. So, for example, displacement ventilation. You have a plenum space under the floor. You're allowing air to move basically in a vertical direction. So as the thermal plume around our bodies pulls the air up and towards the ceiling, we're introducing fresh, non-contaminated air at our feet and exhausting it at the ceiling level. Combined with things like chilled beam and the like, that type of an approach meets both the sustainability goals in terms of energy usage and the goals of minimizing infection control. So we don't have to set this up as a zero-sum game at all.
We could use that very dry environment that chill beams have to stay well below any mold threshold criteria, and all of those practices around a nice dry envelope. I hear what you're saying now. They are perhaps on a Venn diagram, but they needn't be seen as opposing each other. And there are elements that are both good for sustainability as well as good for mold minimization and good for preventing virus transmission.
I think
All
the
right, Brad.
HVAC industry can really lead that charge. I mean, we could tell them and let them know that, no, we could build buildings that meet all these criteria. It's not rocket science. It's proven technology. We're not talking about things that have never been done before. We're talking about buildings operating here in the Melbourne CBD that use these technologies.
I gave you a list of questions that I was hoping we could skip through, and and when I say skip through, I mean walk through, I should say. One of the first ones I think was about yourself and your role, and I think we have covered that. Before we leave that one, though, I'm going to circle back like a targeted missile to just talk about your experience in this hotel quarantine um, conversation. I know it's contentious. I'm not asking for you to, betray any confidentiality arrangements. I am interested, though, in what were the struggles, what were the tensions in the room as solutions were being put forward, and where we are now is that a halfway house? Do you think we've got 90% of the way there? Do you see us invoking or relearning these lessons down the track?
Well, fortunately, there's quite a bit of public information regarding hotel quarantine in Western Australia. As a result of the work I did on the hotels in Victoria, cannot speak about that because I signed a confidentiality agreement. But I can certainly talk about hotels in general, how hotels are ventilated, because I've had lots of experience prior to last year addressing indoor air quality in those types of environments. And there's a lot been published from Western Australia. So I'm happy to talk about it from that perspective, as long as we don't talk specifically about
I'm
Victoria.
interested in that the audience takes away some lessons learned,
Sure.
and if they're in a design meeting, something from this conversation might ignite a new line of thought. So, in my personal experience, we were in my early days involved in a lot of hotels in places like Southeast Asia, North Queensland, and Darwin, and the prevalence of mould there. Hospitals in Papua New Guinea, for example, the prevalence of mould there was almost like this is impossible to defeat. There is mould on the outside of the walls in the outside air. So I know it's perhaps a difficult, it's a full plate of food to talk through or work through, but I'm going to try and keep those three topics of mould, virus transmission, and carbon neutrality on the table. So the implications around striving for mould and virus transmission, we've talked about the approach of seeing this as playing off each other is inherently flawed and designed not to provide a solution. But since the COVID virus has started, what are the changes that you've seen in the industry? Right, the perhaps the line of thinking, perhaps the things that are available as resources. What are those changes, and do you believe they'll be long lasting, or do you believe they're sort of a fad and will unfortunately go the way of many fads?
Well, we do have some concern for and have always addressed ventilation in indoor buildings, indoors. So that has always existed, not as a performance standard, but as a design standard. And the impetus for that really was that 50, 100 years ago, people didn't bathe as frequently as they do now. And if you put a bunch of people in a room, it started to smell pretty bad. So all of the original work on ventilation was really about reducing body odor. And the extent to which carbon dioxide, for example, was a proxy for body odor was one way in which that was considered. But all of the outcomes of that, whether it be ERA or ASHRAE or any other engineering organization that promulgates design standards, has always focused on the initial design, but not any type of performance test or operational requirement. So you have an outdoor air intake that can be varied from 0 to 100%. How you operate it has never been addressed in any type of a regulatory framework. We have had in recent years Green Star, Neighbors, all of the different performance-based building systems that are very much concerned with sustainability that may actually begin to address operation. So that's a private sector function. The market is demanding that. It's not government driven. But we don't have requirements for schools or for government buildings or for any other indoor occupancies where we expect there to be a minimum amount of ventilation. So that's really at the crux of the issue. It's that it's almost like if you go to your local pool and you say, you guys have to put in a chlorination system so that the water doesn't spread disease. But we're never going to check that it actually works. And we're not going to ask you to do daily tests every 2 hours to show that the chlorine level is at a minimum in the pool. And you're not going to have to submit monthly samples for Pseudomonas. I mean, we have accountability systems built into this public health function. We've never built accountability into air quality, ventilation, et cetera. Yet these are things that are important. So not only do we care about infection transmission, but performance, the performance of children in school, the performance of workers in offices. There's very good research that shows that ventilation is related to performance in a wide variety of ways that can be tested, cognitive performance and that sort of thing. So there's a lot of benefits if we had well ventilated buildings and schools and other environments indoors that go way beyond the infection control. But, infection's an issue. I mean, it's not just SARS, it's flu. There's 1,000 people every year who are dying in Australia from flu. There's common cold, rhinoviruses, et cetera. All of these things impact productivity, well-being. They're all impacted by how well we design and ventilate our buildings.
A hot topic at the moment, Brad, would have to be aged care. We have an aging population, and Australia's not alone in this. Other developing countries and developed countries have these aging populations. And as we head into a space where more and more people will be in aged care, do you think there have been lasting changes in that sector? Or if you had your way, what sort of lasting changes would you hope to see? So to clarify the question, what changes have come about recently that you think are really positive or negative? And then what changes would you hope to see, whether they be the same or new ones that we would look after, basically our mums and dads as they retire?
Well, I'm unaware of any changes that have been made in aged care. So you'd have to tell me. But let's step back for a second and talk about aged care buildings where you have often individual rooms, small individual rooms, central gathering places for people. And how do we heat, cool, and ventilate these buildings? Well, because you want to provide people with individual thermal control, and guidelines suggest that's essential. Okay, what solution have we reached? We put split system heat pumps in each bedroom, and the ventilation is provided by openable windows because we permit that in the code. Never mind the fact that we might have 15, 20 air changes per hour when the windows are open and 0.25 air changes per hour when the windows are closed. And we could be talking about schools as well, because I've been doing tracer studies in schools and childcare facilities and other naturally ventilated buildings. And they do a great job ventilating when the windows are wide open. Generally, there's exceptions to that. I've seen, operable windows open in school buildings where they create a flow into one classroom from all the other rooms in the building. So that would be a really bad room to be teaching in or going to school in. But generally speaking, you have very high air exchange rates when all the windows are open full bore. The problem is when you close the windows. So in an aged care home, it's probably one of the worst ventilated occupancies we have. So compared to a public building that has a built-up mechanical system, ducting, airflows, you could argue whether the VAV system is turned way down or not, but you could easily achieve 5-6 air changes per hour in a building like that. But if you've got a building that's depending upon openable windows and the windows are closed, which, in Melbourne is going to happen in very hot and very cold periods, whether it's 30% of the year, 50% of the year, whatever. The windows are not going to be opened, and the attendants are not going to be running back and forth, opening and closing windows in residents' rooms. So basically, they stay closed. So it's no surprise that this is one of the worst environments with our most vulnerable population and our poorest ventilation. And the size of these rooms are generally really small. So, whatever exhalation of infected material is occurring is going to be kind of dissolving around a relatively small volume if the room is small. I think we've seen that. I think we've seen that.
Ventilation system that would use air-to-air heat exchangers, and therefore would maintain the ventilation as a mechanical system, typically at a fairly high rate, 1 or 2 times above what we see in our standard code. I know there are some out there who would perhaps advocate passive house more strongly than that. I'm just trying to give a very general description of passive house generally. So, Brad, with the passive house growth, do you see that um, a passive house approach, which might be very difficult in an aged care facility, but do you see that that is the sort of approach that could really start to address some of the risks of transmission within an aged care facility or a school, for that matter?
Yeah, sure. I think that would be a great approach. I mean, building a tight envelope for air infiltration is critical for maximizing sustainability goals. I mean, people think that you put a lot of insulation in a wall and that's going to make for an economic and energy efficient structure, when in fact the heat transfer resulting from air infiltration is way higher than what's coming from the conductive losses, right? So there's this huge misperception. More insulation is great, but what's most important is actually tightening the building envelope. So that's always a great thing for a number of other reasons as well. We've got perhaps outdoor air infiltration in urban environments where we would like to minimize uncontrolled outdoor air infiltration. One example might be thunderstorm asthma. You had people who were sensitive to pollen, but it had only ever been presented to their respiratory systems as very large particles. Pollen grains are really big, 10 microns roughly and above. So their upper respiratory system managed those particles and they sneezed and coughed, whatever, but they didn't die. But with thunderstorm asthma, all that pollen was whipped up into the atmosphere, exploded into tiny particles, came down, and people thinking that they were protected indoors, like they were when the pollen grains were whole and intact, because they got quite a bit of reduction of infiltration of those very large particles. When the thunderstorm incident happened, all those very fine particles infiltrated. There was time delay, but they came indoors because buildings prevent large particle infiltration, but not micron, submicron, 2 micron. These particles penetrate at reasonable efficiency, as well as traffic-related air pollution. So all the PM 2.5 that we're concerned about and ultrafine particulate associated with diesel emissions, other power plant emissions, whatever, that is also going to infiltrate indoors. So reducing infiltration not only has energy benefits, but it has potentially health benefits if, when we introduce the air through an air-to-air heat exchanger, we provide some filtration.
So, Brad, just seeking an opinion then, what sort of minimum filtration rates do you think would be sensible? keeping in mind when we get up to things like F8 and F9, we're dealing with fairly high pressure drops that may not be easy to retrofit. Um, are we thinking F5, sort of down at the 20% efficiency rate? Is that what's your sense on our filtration grades? And I'm just suggesting here we're looking for an opinion. Nobody's, I think, going to go out and write a specification tomorrow morning on this, but it would be nice to know where is in that curve of cost versus performance, or effort versus performance. Where do you think the sweet spot sort of lie?
I think it's important to recognize that filtration isn't an all or nothing thing. It's a question of efficiency at different particle sizes. So a lower quality filter, so to speak, is still removing a percentage of the very fine particulate. When we grade filters, we talk about the particle size that has the most penetrating ability, 0.3 microns, because there's maybe 2 or 3 different physical forces that govern deposition of particles on a filter. And one of them is the actual, what we think of as a particle of a certain size getting caught because it's passing through a matrix of things that have holes smaller than that particle. But there's other types of physical forces at play. So even a quote unquote lower quality filter is making a big impact. And while it may only have 50% efficiency at a particular particle size, it has 50% efficiency. I think that, for example, we saw that with some of the portable air cleaners that are being introduced for COVID. And of course, everyone says, we want HEPA filtration. Great. But if you put a filter that's less efficient than true HEPA in a room, and you put 3 times the air through it than the HEPA filter, every time that air passes through, if there's 75% capture efficiency, the first time there's only 25% left. The second time there's only 6% left. The third time it passes. So there's more to the story than just the efficiency of the filters. Yeah. And then again, it's also worth thinking about the size of the target particulate. That's important.
That is important. I'm thinking back now to the events of the Sydney bushfires, which, given our last few years, I think some people might have already forgotten the red haze and the photographs, almost the dystopian photographs of the Sydney Harbour Bridge and the bushfire particulate that was in the air. Now, those particulates were down at the PM 2.5 range. There's no point having PM 10 in to filter those out. Well, sorry, not as much value in that as there was in having the fine PM 2.5. When we go to look at, say, weather stations, and you ask for PM 2.5 data, it's very rarely provided. I think this might be something that in a future-looking infrastructure we should see more of. It is important to know the temperature and the humidity and the wind speed and direction, but I would have thought it's also important to see PM 2.5 levels. Do you know of any moves around perhaps expanding the Bureau of Meteorology's range of variables that they're looking at?
I actually did a project that would involve a legal case where I needed to establish PM 2.5 exposure for someone driving on the highways around Sydney. And there actually is quite a bit of PM 2.5 data at most of the air pollution stations, the fixed stations. There must be 10 or something like that throughout the Sydney metropolitan area. So I was able to pull that PM 2.5 data on an hourly basis, and perhaps even more frequently than that. I don't recall exactly. But I think there is quite a bit of that data out there. Originally, we were talking PM 10, but I think over the years, last 5-10 years, there's been a push to look at PM 2.5. And I think we'll probably see a focus on ultrafine particulate as well going forward.
But that's excellent, and thank you, Brad. I wanted to dive into a couple of other ones. We've touched on this a lot already, and I suspect I know your answers. I asked you to consider the relative pros and cons of mechanical versus natural ventilation. And I think you've leaned fairly heavily on the very strong pros for mechanical ventilation. What are, in your mind, the pros and cons for natural?
Oh, that's a good question. Because when the windows are open, it can be very pleasant, assuming the air outside is not contaminated. Assuming it is fresh air, you're going to get very high air exchange rates. I've measured using, I have a setup for doing sulfur hexafluoride tracer gas studies, and I've measured buildings with the windows open and with the windows closed. Sometimes it's 150, 250, 600% improvement in ventilation with the windows open. Sometimes it's the air exchange rate is so rapid, I have a hard time measuring it because my tracer levels fall so rapidly. I can only get 2 or 3 measurements in at each of 6 locations in the building before the levels have fallen below 100 part per billion. And my threshold for detecting SF6 is around 200 ppb. So the thing is, only those buildings when the windows are closed. So then you think, what are some solutions for that? So, for example, we haven't paid enough attention to upper room germicidal UV. It's a technology that's been around a very long time. Depending upon the wavelength of the UV that's used, we have to protect the skin and eyes for certain wavelengths. There are some new technology coming along that perhaps will use wavelengths that aren't as biologically of concern. But the issue here would be exposure to people's eyes or exposure to people's skin. But most of the deployments in the frequencies of concern are done with louvered source directionality, so that the upper room is bathed in the UV light, but there's no UV light coming down impacting the occupants. Now, no, yeah, are addressed. So that's a professional installation. It's not a do-it-yourself kind of a job. It has to be done properly. And if you do something like that, because of the way the small particles float in the air, the ones that are floating in the UV bathed zone are going to spend a long time there. And deactivation via UV for unshielded viruses like SARS-CoV-2 is really excellent. So if the air spends a bit of time up there, or if the intensity of UV is extremely high and the duration of exposure is short, as long as the dose is sufficient, we'll inactivate those viruses. But it's worth keeping in mind that ventilation does a couple of things. It exhausts viral particles, or it exhausts particles which contain active virus. It gets rid of other particulate floating in the air. It gets rid of vapors and gases that might be present. So when we go to, for example, portable air cleaners, we do nothing for the gases and vapors in the air. And when we go to upper room GUV, we retain our ability to deactivate pathogens, but we lose the ability to remove other particulate, and we lose the ability to remove gases and vapors.
I think you make a very good point. Sometimes we see some of these viruses as difficult to kill. But I recall in some of the work we were doing in Papua New Guinea, they were suggesting that only 7 seconds of sunlight on TB particles would be sufficient to, in effect, kill them or inactivate them. So perhaps we don't need quite as much contact time as we may imagine, or as you described with the filtration exercise, repeated short exposures may be sufficient to sort of wear down the virus.
Mm-hmm. Yeah, because if we're spending 3 hours in a room and somebody has been exhaling into that room for several hours before we arrive, the room is filled with small particles that are going to basically circulate around. Some will deactivate just by virtue of the fact the virus dies over time. Some of those particles will deposit on surfaces. but the remainder are going to float around. So our duration of exposure has a big impact on, our dose and the likelihood that we might become infected. So if you can circulate some air through a filter, even if it takes multiple passes to remove those older exhaled fine particles, you're still going to reduce the ambient concentration. You're still going to reduce the infection potential, whether it's a high efficiency HEPA filter or something a little bit less efficient.
Okay. Well, listen, Brad, I might just sum up and ask you to correct me if I've got some of these summaries wrong. We started this podcast with a conversation that really the goals of sustainability need not be at odds with the goals of virus transmission or mold minimization. That there were a number of sustainability tactics and technologies that have been in alignment with managing dampness and, of course, keeping fresh air rate proportions high. We talked a bit about sort of the changes in the industry. And I think you raised a really valid point around the idea that, buildings have fire testing and people report on those. We have drinking water requirements of local health authorities and people report on those. Even swimming pools, they do record various ORP levels throughout the day. So the records are available for inspection. But with air quality, we don't have that obligation. We have a series of sensors, and maybe they're calibrated and maybe they're not, and maybe they're controlling the fresh air intake and maybe they're not. I think too we started to talk about the choices between mechanical and natural ventilation, and you leaned fairly heavily, if I can paraphrase, your opinion on mechanical ventilation, primarily because of the ability for us to get a high level of dilution as well as filtration in, but also to minimise, I think, the risk of perhaps what I think you called it thunder asthma or thunderstorm asthma, and that event where a lot of pollen got swept up into the upper atmosphere, basically got atomized, and then once that fell on the community, natural ventilation systems were quite susceptible and others weren't. You did speak.
Well, I think many were, susceptible.
You mentioned that natural ventilation does have a strength in obviously the extent of dilution that's available, but obviously nobody filters out air that comes in other than a fly screen, air that comes in through a window. So I think one of the things that I took away from our conversation was also certainly Passive House has a lot of strength and can be applied to a lot of different types of buildings, such as school and aged care. And I think you saw that aged care has its own challenges, primarily because of how their accreditation guidelines require or encourage people to have large amounts of the space air conditioned. So there's a remaining item. I'm presuming that the way we could tackle aged care ventilation could resemble the way that you've been promoting we tackle hotel quarantine. In terms of pressure differentials, reasonable levels of dilution, and where people may need to be isolated, for lack of a better word, is maintained as an extraction system. And therefore, the idea that we naturally ventilate through the edge of an aged care facility is actually a weakness, even though it may be saving money or energy. It is a weakness because it may take away from the ability to keep the room under a negative pressure in comparison to the corridors. Have you got any gems or any words of wisdom to add?
Well, you hit upon a number of things. I mean, ventilation becomes relevant when we talk about infection control. Ventilation becomes relevant when we talk about moisture management indoors. And I say that as an American in Australia, outdoor air and removal of all contaminants indoors. So we're not just talking about removing particles containing infectious disease from respiratory fluids, but we could be talking about removing particles associated with cat dander and dog hair and cockroach allergen, et cetera, on and on and on. So our indoor environments can use better filtration. They could use better infiltration of outdoor air. All of this is a very positive thing. As a society here in Australia, we invest a massive amount in our housing, in making it beautiful and having gorgeous countertops and beautiful spaces and ceiling moldings and all the things that we spend money on. I think there's a real demand at this point from people to have a healthful environment be one of the key criteria. And I think the first place we'll see those change coming from is from the private sector. I doubt that any impact on residential housing will come first from government regulations, but people will vote with their dollars and they'll look for housing that addresses these concerns as much as addresses other aesthetic concerns. So I think the fact that this whole issue of ventilation has become so prominent with COVID will have nice spillover effects in terms of making people think about how we manage moisture in our homes, how we manage particles in our homes. Because you go back to the house, the typical Australian home of 50 or 70 years ago, double brick construction, leaky as a sieve, no management of indoor kitchen moisture, little management of bathroom moisture. Even in recent years, exhausting bathroom air into the roof cavity where it's going to condense on the underside of the tiles or some other place like that, as opposed to directly outside. These things can all be improved, you know. So there's a real opportunity here to do things well and to do them in a way that is both sustainable and protective of indoor air quality. So we design a passive house, we reduce infiltration to next to nothing, but we manage the flow of air in. And clearly, if you build a very tight house and you don't manage moisture, you're going to have huge problems. So part of the approach is that, yes, you do exhaust from your kitchen, but you exhaust effectively. You build hoods and fan systems that actually work really well. Not, for example, the kind that take the air and remove a little bit of the smoke and recirculate it back into the kitchen, right? And we exhaust dryers and we exhaust the air in bathrooms. And we manage the moisture very scientifically and very appropriately. And all of that is consistent, with both sustainable and air quality goals. And there's a lot more to it too. If we have a passive house and we're using cleaning products that contain citrus-based agents like limonene and terpenes that react with even ambient ozone, we better have good ventilation in that space all the time. Because when we cook, when we clean, we're also producing particles. We're also producing gases and vapors. So all of that has to be intelligently managed. We have these tools. We just have to implement them.
Well, Brad, that's a good place. That's a good place for us to finish on. I think there's some hope there. There are proven technologies within reach, and I think the most pleasing thing that I took away from this was the alignment of both sustainability and COVID and mould. I mean, nobody really wants to be put into the position where they need to make a choice of one over the other. But notwithstanding that, I think there's been a very fruitful conversation. Just in closing, I'm hoping that you could just give a 10-second plug for your work with ERA on COVID-19 guidelines. Would you mind just letting the listeners know what you've done there?
Sure. I've been a speaker at a number of ERA conferences coming up and in the past. And at the end of last year, 2021, I authored a document on ventilation in schools, which talks all about some of the issues with infection control and tries to approach it from the perspective of a school administrator. So not so much a technical document for designers or engineers, but something that's intelligible and addresses the concerns of school administrators. But I think because it's very broad in its approach, the applicability goes well beyond schools. So anyone dealing with any building, I think, can learn from that. And that's available on the ERA website. It's available on my website at Prezant Environmental as well, but I think you could easily pick that up if you just Google Prezant ERA. or Prezant era COVID or something like that, you'll get that document.
Well, again, Brad, you've done me and this podcast a tremendous honor by giving me your time and for having these conversations, however awkward they may have been. I thank you for that, and I wish you well, and I'll talk to you soon.
Thank you so much.
Bye-bye.